Okay, so it doesn't really matter to me how you calculate this. In science, you will learn something called stoichiometry, and I've shown you it a couple times. It's not a technique that I need you to know this second, but it's a way that you can kind of calculate things fairly easily. So if you're buying a $1,000 bike, how many of them, or how many days could you do this? If you said I've got $1 million over, I don't know, one jackpot, whatever, and I'm trying to figure out how many days I can spend $1,000. This is in dollars or CHF, whatever. And if you could say I'm spending $1,000 in one day, right? I might do this, $1,000 for one day. I put the dollars on the bottom so they cancel, just like fractions do. Like that and that cancel, the units cancel. This is called dimensional analysis because you're messing with the dimensions. And so now I've got this many days. If you divide this by 1,000, it tells you how many days you can burn through $1,000 a day. It's 1,000 days, right? And then you can do the same thing. If I take, days is fine. That gives me, 1,000 days? I don't know. Can't really visualize that. So let's switch days to year. I know that 365 days is 1 year. I'm going to put days on the bottom. 365 days equals 1 year. These cancel out, day and day, and you're just left with years. This technique is really nice because I don't have to think about, do I divide or do I multiply? It tells you what to do because I start with $1,000 on top, dollars on the bottom, they cancel, days on, and then I can say, okay, which direction should I put this, days or years? It just helps you decide multiply or divide. I'll show you it a couple times as we go through this unit. It's probably one of the most useful mathematical techniques I've ever learned. I learned it in chemistry, to mess with moles and all that stuff. Anyway, I got about 2.7, something like that. So it's 2.7 years. Maybe one day you forget or whatever. Let's just round it up, just because we're trying to get a sense of this. Let's round it up to 3. Is that okay? Yeah. All right. That's $1 million. You could spend $1,000 a day. You could buy a bike a day, or skis, or whatever costs $1,000. A new PlayStation? I don't know. For 3 years. Think about what you were doing 3 years ago. You were starting 6th grade, something like that. It's a decent amount of time. Can you imagine throwing down $1,000 every day? Just what you could, all the stuff you could have for $1,000 a day for that last 3 years. Pretty sweet, right? If you had $1 billion, it's going to act similarly. $1 billion. I know this is, this is the same thing. It's a 1. That's a million in sort of American British vernacular. That's $1 billion. I know it goes million, milliard, billion, billiard in kind of French, Spanish, maybe even German, something similar. But in the British English language, million is 6 zeros and billion is 9 zeros. So we'll just kind of try to consolidate whatever you call this. If you have this many dollars in your pocket, how many days, how many years can you burn through $1,000 a day? Try that one. Whoa. I'll show you my technique again, but you can do it however you like. I'm going to do the exact same technique, $1,000 a day, francs or whatever, and 365 days in 1 year. I got not 3 years, but 3,000 years, right? It should be 2.7. We added 3 zeros, so you just add 3 zeros to that effectively. So I'm going to round, and instead of 3 years, if you have $1 billion, you hear about billionaires. $1 billion. You got $1 million in your pocket, you can buy an apartment, right? If you have $1 billion, that's significantly different. 3 years you can spend like $1,000 a year for 3 years for $1 million. That's great. But the difference between $1 million and $1 billion, whatever words you use to associate that many zeros, is going from 3 years to spending $1,000 a year for 3,000 years. Do you know what's happening 3,000 years ago? That. Like, they were building pyramids. The equal sign wasn't invented. The zero wasn't invented. Like, 3,000 years ago, that was happening.
It's like 34 of the average lifespan.
Ooh, there's 34 generations. That's good. Did you do like 80 or 75? Yeah. I love it. Okay, so here's the next little bit. Who's the richest man on Earth? It just changed. Bezos just overtook him again. This has been back and forth. Just a couple of days ago. But Elon Musk is not far behind, and like at that point, so I just looked. Bezos is Amazon's guy. He's not Amazon anymore, but either way, he's worth $200 billion.
Oh, eat the Richest, swear to God.
How many years can he blow $1,000 a day before burning through that? Try that calculation.
He should not exist.
He should exist, but he should just like give half of that away. Philanthropy. Look, they're all philanthropists.
It's called tax cuts.
So calculate 200 billion. How many years?
547,000 years. 550,000 years.
If you're doing this numerically, here's 200 billion. It's 200 and then 9 zeros. 3, 4, 5, 6, 7, 8, 9, right? And you do the whole stoichiometry again if you want. But we also know that it's how much more than this?
1,000.
200.
200.
Yeah. So how much more is it than this? Yeah. So you'd go 3,000 years. 200 sets of 3,000 years. So 6 and 3 zeros and 2 more zeros. 1, 2, 3, 4, 5. 600,000 years. What was happening 600,000 years ago? Who was? Yeah, right. This This is Homo heidelbergensis, Homo neanderthalis. People don't exist this long ago. Like, these are not people. These are like bipedal things that kind of look like people but are not people. And so if you have $1 million in your pocket, you can burn $1,000 for 3 years. Which, like, think about 3 years ago for you, fine. Bezos can burn $1,000 back until people don't exist anymore. Like,
it doesn't really do you any good when money is
yeah, you're like, I'll give you like a big fat blue 100 from in Swiss francs. They're like, oh, they use it to start a fire. I think that's amazing. What's really hard, like, our brains are good at counting this many things. And if you have double this many things, you take off your shoe and count toes, right? Our brains are good at counting integers. This doesn't make sense to us, right? Like, we are not built to understand this. And that's why we use some things like, we'll come back, scientific notation, right? It's ways to simplify numbers to make them a little bit more approachable and also to make their manipulation easier. So scientific notation looks kind of ugly, but often when you're multiplying or dividing big numbers, it makes it a lot simpler, and I'll show you why. Have you seen some scientific notation?
Yes.
Great. So let's cruise through what scientific notation is, just really briefly, and then mostly I want to show you how to manipulate scientific notation, like multiplication and such. So that's 3,000, right? And if we were trying to change it to scientific notation, you could say, I'm just going to breeze through this because it sounds like you guys are good at it. 3,000 is 3 times 1,000.
Yeah.
And 1,000 is 3 sets of 10. 10 times 10 times 10, right? 3 zeros means 3 tens. So this is 3 times 10 to the third. Yeah? You could also write this as 30 times 10 to the what?
2.
Yeah, great. That's not in scientific notation, right? Because this isn't between 0 and, or between 1 and 10. Yeah? That's the only, like, fussy little bit. That is the same number as that, is the same number as that, but this one is in, like, nerd-friendly high five. We put it in scientific notation. Don't look. What number is... See if you can write that one in scientific notation. I'll show you kind of a shortcut to do so. You write it. You do it. I don't want you to... All right, bring it back. Bring it back. So this is a 4, right? And one way to do this is like the little jump method, where you say, here's the dot, and you go 1, 2, 3, so times 10 to the third. That's great. That's the shortcut. You're right. It works. And so this one should be 1, 2, 3, but negative. So I'm guessing this is 4 times 10 to the negative 3. This is what's actually happening, though. This isn't the 10th place. This is the hundredths. This is the thousandths. It's good that I have a mask on. So this is really 4 times 1 1,000th. Yeah? And we've seen with the negative exponent that 1 1,000th is this number, but because it's in the denominator, it's got that negative on it. That's physically what's happening when you're moving the decimal over. Do the decimal trick, absolutely, but know that that this is why. Right? Great.
So 1 over 1,000 is equivalent to 10.
Yeah. Yeah. All right, you guys are good at that. But boom, there.
What was that, sir?
Try these two. Build me that one in scientific notation and that one in scientific notation, and then we'll go. Mr. Gilead. He likes scientific notation because he's a science nerd.
So it's 45 times 1, 2,
Jump.
Chest. It's 45. It's like 5. It's 45. It's 45.
Cool. Physically, what's happening is you're saying 40. Well, here's kind of the long way. 45, and let's see. 1, 2, 3, 4, 5. So times 10 to the 5th, right? And then we kind of switch this around to 4.5 times 10. That's this piece. This is kind of just a way to look at it. And here's a 10 to the 5th. So this is really 10 to the 6th. Which is 1, 2, 3, 4, 5, 6. Right? Do the jumpy thing. That's fine. That's fine. Similarly, this is going backwards. 1, 2, 3, 4. So 5.92 times 10 to the 4, negative 4, because it's going backwards. I won't belabor the point. Sounds like you guys know what you're doing. Yes.
Why do I have to use 4.5? Why can't I use 2 to the power of 2, 3 to the power of 2, and 2 to the power of 3?
For this?
Yeah.
Because
45 is broken down into 9 and...
You could. We still want we want an easy, useful number. And so we already have enough multiplication and such going on. So we want this number to be between 1 and 10.
So it doesn't matter if you use decimals in it.
Yeah, it's fine with decimals. And I'll show you why we use those
How many
in a second.
decimals is okay until you have to do what you do for B?
It's user's choice. It's user's choice. All right. So this is the reason we like multiplying values in scientific notation. We like scientific notation in science, partly because you can express large numbers really easily, but also because they're easy to use. This is probably too much work to change it into scientific notation and then multiply, but I just want to show you it as an example. Like 2,000 times, 40,000? You'd multiply those coefficients, and then you'd multiply the numbers of zeros, right? So this is 3 and 4, so you'd have 7 zeros, right? we're going to do the same thing in a second. Give me a second.
It's so filling.
What's that?
It's so filling.
Resin. This is 2 times 10 to the third, right? 1, 2, 3. This is 4 times 10 to the fourth. 1, 2, 3, 4. Good enough. What's nice about this is that it's all multiplication. This times this is kind of like saying 2 times 3 times 4. That's 12. That's 24. And even if you go 3 times 2 times 4 and switch up the order, still 24. And 4 times 3 times 2, still 24. It doesn't matter the order. And so what's kind of nice is that you could switch this up to say 2 times 4 times 10 to the third times 10 to the fourth. This gives you the 8. This gives you 10 to the 7. You don't have to switch this around. You just go coefficients, multiply, there it is. Powers of 10, multiply, add the exponents, there it is. So jump right from here to here. All right, take that, try it with this. Maybe consider this as 1.5. So switch it to the scientific notation, and then try to multiply. Too easy. Alright, so I just switched it into 1.5 times 10 to the fourth, 2 times 10 to the third, and I'm going to multiply those coefficients. So that's 3, which is nice, and then this is 10 to the 7. In this case, maybe it's not worth doing that, because they're fairly easy numbers, but when the numbers get kind of ugly, it's easier just to multiply the coefficients, multiply the powers. Cool, moving on. Why don't you try B? Because we just kind of did something like that. B.
Do the tens plus one?
Sort of.
2? Can you subtract them? Yeah, they do. It's one of the laws. You put them up like this, and they can be like this is easier just to not stack it. I'll show you the parentheses laws.
What do you sense that you can do from that? Yeah, right, they're just fractions, so you can call this 8 over 2 times 10 to the 5th over 10 cubed. So this is 4 times 10 to the, thanks, times 10 to the, subtract those 2. Cool.
How wide is your class?
Because there's 5 tens of them, like 2, 3, 4, 5, and there's 3 tens down below. Like 1, 1, 1, 2 left over. Cool. That's what we did yesterday.
So you can't subtract. So does
What's that? Well, because it's still this thing times that thing. Okay, and this multiplication is still here, so you can kind of leave it like that if you like. Cool. All right. Let's try it with your calculator because most of these we're doing with calculator. I want to show you how to interpret what the calculator says to you. So grab your calculator. Let's do B together on this one too. The hardest part of this is just inputting it. So we'll try to be careful and input it together. And so let's call this 9 point, parentheses, right? Well, it's 9.49 there. And then times 10 to the You can say times 10 to the, there's a shortcut that I'll show you in a second. -3. Use the negative, not the minus. Oh, we're going to drive by. We're going to drive manually. A little fussy, right? Hit the divide, open parentheses. Parentheses are right here.
They're above 8 and 9.
No, but they go small.
Yeah. You need
Same.
to click the
Then
side
you click
button.
up
Click the
or
side button.
left or right.
Which side button? This button. And then
Yeah,
it goes.
click over, this over button, and then it'll pop down again. Right? A little fussy, but
Doesn't work.
yeah, what's up with that E?
Okay, type it. See, now it's up here, right? So I just typed the 6, right?
Yeah,
It's a small
right?
letter, like there's
So-
a big one.
So, no, it's not error. Think about like 2,000. There's 2,000. If you say 2 times 10 to the, what is this, 1, 2, 3? You get 2,000. If you say 2, if you look right here above this comma, it says EE. It means like a times 10 to the exponent. And so if you put E3, the E means times 10 to the, you get the same result out. Right? So your calculator, instead of writing times 10 to the, will write 2E3. So that's what this means.
So
up here.
It's like to the power of.
Yeah, it's
E to
times
the
10
power.
to the power of.
So is
So
it
this-
3.652?
Why is it
You also
shown
get this.
as 3 and then like square and not circle as a number behind it?
I don't know. It's the calculator's
I'm about to type the
vernacular.
rest of it.
Right? That's fine if you're like working through stuff, but don't leave your answers like that with an E in it. That's robot
So
language,
it's-
and I don't speak of that language, right? So always convert that to times 10 to the -9. So that number is this number, and that's what I want to see on your papers when you're done.
Wait, so is E 10?
Scientists don't write like
Yeah.
that. They'll switch it around.
So E is power of.
E is times 10 to the.
Okay.
But why even bother with the E?
I think they do it to truncate things because when do you see like they put in this when I put it in, it just takes up so much space. So my guess is that they put it in there to shorten expressions, especially since like now this is like a newer format that can actually do these exponents. But I think beforehand they were using this sort of thing.
It's 10 to the power of.
So they have to write this out
E
as
minus 9 is 10 to the power of
3.65 times 10 caret parentheses -9. So they just said 3.6 and write something that makes me know that it's doing all of this stuff.
Yeah.
That's my guess. But it's just hung around as a little artifact. Jordy!
So on the calculator, you just put you just put it like you would normally.
Yeah, I just want you to see where the buttons go. All right, try this. Take 2 of these. Doesn't matter to me which ones. Switch them either from standard notation to scientific. Standard notation, like turn this into standard notation, meaning all of the zeros, and then turn this one into scientific. And then also I gave you a little hint what that number represents. So try to pick 2 of them. Like either like pick this one and this one, or this one and this one, doesn't matter. They represent something different, either small or
What was that?
big.
3.65 times 10 to the power of 9. Do you just use your calculator for standard notation?
That's one way to run it. You can just pop that in your calculator, and sometimes it'll give you the whole thing. Sometimes it won't, right? But I will probably ask you, yeah, I mean, that's like a kind of a 1 and 2. But easier than that even, like it doesn't require a calculator. You just move that decimal place, 1.6, move it 11 spaces that way to make it a small number, 1, 2. There's the dot, and then fill in your zeros. It turns out to be that. Oh, avert your eyes. Avert your eyes. Okay, so this first one, 1.49 times 10 to the 8th. Like, how many decimals do you keep? That's all criterion D stuff, right? A couple of times, there were a couple of you on the criterion A that wrote like a billion decimal places. That's annoying, right? I don't really care on criterion A's if you use like 2. I'd probably round this up to 1.5 times 10 to the 8. But as long as you don't use like a billion decimal places, I kind of annoyed you with criterion C on the last one because we were using trig and there were a lot of decimals. But that's all like criterion D stuff. Yeah.
I feel like for the first one, you kind of need to have the decimal places. If you round up, you're gonna be
You're gonna lose
600,000
You're gonna
kilometers off.
How far do you think this is? What do you think that number represents?
Width of our solar system.
Distance from Sun to Earth?
Yeah, you're skipping a couple planets if you're gonna round it up.
You're like, Mars, this isn't the Sun. That one turns into this gross number, and that's about the diameter of a bacterium. If you're into that stuff,
There's 9 zeros in
that turns into this number. What do you think that one is? About the diameter of a human hair, the thickness. Yeah, tiny, right?
How many
I'm
zeros are
assuming
there?
the last one's light speed.
6. Yeah, there you go. Last one is speed of light. Bing. In space, in the vacuum.
Does it change if you're not in space?
Yeah, that's why. Yeah, that's why if you take a pencil and put it in a glass of water, it looks broken because the light changes direction. It's called refraction. Physics. Take physics course. It's great. Yeah, and so you can see like it changes as it comes out. Well, it's a big part of physics, but as it comes out, it changes speed, and that makes it bend a little bit. Kind of cool. Cool. That is scientific notation. I think it's short and sweet. Jump into that. It's 2C, but it's the stuff that says scientific notation. Stop when you get to the next part. I'll bounce around and give you a hand. You got about 10 minutes.
You were there.
We'll get out of here after
The
that.
rest of the